Recording in progress. Now I need to turn on the video. There we go. Okay. So, so after class, I'll try to help answer questions about the homework. But the starting point in all cases is going to be to define the system. And usually, if you can, you try to make the system be so that there's no outside force acting on it, if you can, so that the impulse is zero. And I'm going to try to see this. All right. Okay. So today we want to turn to kind of our last subject, namely rotational motion. We've already seen this quite a bit, well, a little bit. And so I'm going to kind of go back and do a little bit of cleanup, a little bit of review. So it's kind of a bit of a review, a bit of new, and kind of emphasize some things that I didn't emphasize before. It's not necessarily harder. Just be on. Just like a 3-volt battery. It's not. Okay, so that's the plan here. So I apologize. I think a lot of today will either be some mix of review or obvious, because it's mostly just properties of a circle, at least at the beginning. And then we will things will kind of progress a little bit more. And then the plan is to talk about moments of inertia on Friday, and then torque and on Monday, Tuesday, and then static equilibrium problems on after that. Okay, so so I want to go back. Let's talk about circles. Okay, this is not hard stuff. You guys all know, but and we talked a little bit about this, but we're kind of laying the foundation to be able to talk about rotational problems. So we got to go back to the beginning. So going around the circle, there are different ways you can think about it. You can think about motion along a circle, kind of like you would. You can think about a unit circle. Okay, so you could do that. In that case, lay an XY coordinate system on top of it. You could talk about points on a circle in terms of X and Y. So if it was a unit circle, maybe you guys remember this from, is that pre-calc? Is that when you do unit circle stuff? I don't know. What do you, on a unit circle, how do you determine the X coordinate of a point on the circle? You guys remember? X and Y, no? So if I have a point on a circle, usually introduce an angle. How would I choose X and Y? What would that be on the unit circle?
Do the sine and cosine.
Sine and cosine, yeah, which one goes with which?
Sine.
Cosine with the X and sine, right? So if you do the angle in the quote unquote normal way with respect to the positive X axis, we would write out this point, that's visible, as cosine theta and sine theta, X and Y, cosine sine. All right. What if the circle wasn't a unit circle? What if it was circle of radius r. So if you stretch it out, what would happen to your horizontal and vertical positions if you just rescale everything by r? They're just going to be bigger by a factor of r. So you just multiply everything by r. That would give you, for a circle of radius r, that would give you x and y. So we could do that. Sometimes that is useful. That's not the only way. So you have a point, it's in 2D, so you need two values of x and y, but because it's on a circle, there's a constraint. So really, x and y aren't independent, right? Both are functions of one parameter, the angle. Because even though you're in two dimensions, they are constrained to live on a circle, so they're not independent. So we could write out points of a circle that way. The other way we can think about this, or there is another way we can think about this, namely in terms of arc length. So starting here, you could also think about your position on a circle in terms of arc length. What symbol do mathematicians use for arc length? Like here.
S.
S is very common. Sometimes people use a lowercase l. Okay, they're different for length. Okay, I'll use S. I think that's what at JCC the mathematicians use. S, or sometimes they use script like a cursive S. It's faster, right? So we could also describe the same motion or the same position, I should say, in terms of arc length. And how do I relate S to theta? Does anyone know the relationship? No? Okay. So to figure this out, we're going to use the most powerful mathematical tool we have, or technique, namely guess and check. So if the angle is 0, what's the arc length we get?
0.
Okay. Nice. Okay. If the angle is 2 pi, what is the arc length?
2 pi r.
2 pi r. If the angle was only pi, only halfway around, what would the arc length be?
Pi r.
Okay. I think we're in a position to make a guess. Can we guess the general formula relating the angle and arc length? What is the general formula? Well, notice if I have the angle in radians, right, so that's important. If I have the angle in radians, the arc length corresponding to that angle is given by the angle multiplied by r. Where the angle is in radians. How do you go back and forth between radians and degrees?
180 over pi.
Okay, 180 over pi. or 2 pi 360, however you want to think of it. If you have to do it in your head, how would you estimate it? Well, what number do you wish pi was? 3. Right? So 180 over pi becomes 60. So if you had to, that's what you would choose. In reality, it's what, 57 or something. But you can kind of estimate that way. So there you go. This is the relationship between arc length and angle. So we were talking about things that rotate, and sometimes maybe you want to go back and work out X and Y coordinates. Other times, maybe you want to work about with lengths tangent to a circle. And most of the time, we will translate all of that into statements about the angle. This will form our bridge that connects linear quantities to angular quantities. Okay? So remember this formula. Let's come back over and over. Let's take an example where this might be useful. Let's imagine we had a road and a tire. And let's say that the tire rolls without slipping. And let's say the diameter of the tire is 2.5 feet. Why 2.5 feet? Because I'm a jerk. And so what I would like to know is how far does the tire move if it rotates through, let's get a real jerk, 620 degrees. Okay. So if it rotates through 620 degrees, how far does the tire move over? First thing you have to do is a whole bunch of conversions. You've got to convert degrees to radians. You've got to convert feet, meters. Yeah, so I want the answer in civilized units. Do all those conversions. Let's see what we get. Okay. So how do we convert the angle to radians? Okay. Yeah. units. Put labels down. Put labels down. If you want to, write the letters, write radian, rad, just as a placeholder. So you get the fractions in the right order. One, how many radians? So you're converting this to radians. What's the conversion? Go, how many degrees would 180 degrees? Sorry, but what would that be? Sorry, how many radians? Pi. So pi is 180. Pi radians is 180 degrees. So you have pi radians divided by 180. Put the labels down so you get that right. So, okay, you know how to convert the angle to radians. All right. Let's go through this. So where does the conversion come? It's just a unit conversion, like pounds to kilograms or length, inches to centimeters. Okay, so in this case, maybe these simplest one, you know that traveling 180 degrees, so 180 degrees is how many radians? How many radians is a half turn? Pi, right? You got to know that. Or if you don't remember that one, remember that a 360 rotation is 2 pi, but you got to know one of those two. Right? So that's, well, not approximately, it is equal to pi radians. Now, radians, it's kind of a fake unit. It's a placeholder for a unit in essence. But you might as well just write it. Okay, then it looks just like unit conversions that you're used to. All right, so then, okay, so if they're the same, then I can form a unit ratio. 1 equals this divided by this. It's a unit ratio. It's pure number 1. There are no units left. If this equals this, then when I divide them, I get pure number 1. Full stop. And then you can just multiply that as many times as you need to convert units. So in this case, I have 620 degrees, and I multiply by 1, but I write 1 in this handy way. And then I get my conversion. So I get 620 times pi divided by 180. .82 radians. I usually write rad just to remind myself. All right. All the radians, again, I emphasize radians really are kind of a fake unit. They don't really have it. Sometimes, I mean, you would not be wrong if you just left it as 10.82 with no label. But just because I make it feel good, I label that. All right. How many people were able to get that on their own? All right. Then we have to convert 2.5 feet. That's a unit conversion we've been doing. 2.5 feet. Okay, if you want 3 digits, you've got to, if you don't just remember things, you've got to convert feet to inches, inches to centimeters, centimeters to meters. What do we get when we convert that?
4.2 meters. No, okay.
For the 2.5 feet,
0.3.
0.762 meters. That's the diameter. Okay. Because 3 feet is a yard, and a yard's close to a meter. So if it's 3 feet, you'd get approximately 1. Well, this is less than that, so I expect something less than that, but bigger than that. So that seems reasonable. Now, that's the diameter. What would the radius be?
0.38.
Yeah, cut that in half. So the radius, 0.381 meters. How many people were able to get that? 0.381. Up to round eight. You know, if you did it, if you only kept 2 digits or something, you know, that's not what I'm. All right, awesome. So, tire rolls without slipping. How far does the tire move horizontally if it rotates through that meter? Which sentence here, or which clause is oddly specific?
Without slipping.
Yeah. So if I write something that's oddly specific, there's a good chance it's for a reason. Okay. So why is the rolls without slipping piece important? So here's the thing. I gotta do this. All right, I've got. I won't use the string. What I want you to imagine is that there is a string that wraps around this. Okay, and imagine that as it rotates, it just unspools the string. Okay, so the string is just going to, you just keep track, and what you can hopefully see is that the amount of string that is unspooled is equal to the arc length that comes in contact with the ground. But that's equal to the arc length that is kind of swept out by the rotation. So what you're getting, if it rolls without slipping, the side-to-side motion is the same as the arc length unrolled, or they're the same. If I don't say that it rolls without slipping, you could have this. How far did it move sideways? 0. How far did it? But it spun, right? All right. So if I don't say rolls without slipping, you really can't answer, right? Because maybe it was on ice, right? Maybe it's happening in space and it didn't move anywhere. Or if it did roll without slipping, then they're 1-to-1. So here's the thing: rolls without slipping is like a code word. It allows you to take 2 things which could be separate, the side-to-side motion and the rotation, and it allows you to say that, oh, they happen in lockstep. That's good because it means you have 1 less variable, it means it's less algebra to do. It's easier. Right? So rolls without slipping, look for that because that clause helps you a lot in problems. And it looks innocuous and you just skim over it, whatever, but it's important. Okay. All right, so rolls without slipping tells me that if I know the angle, or is not the angle? Well, the angle is going to tell me the arc length, and the rolls without slipping tells me that the arc length is the same as the distance. That's the key insight there. All right. So now I just pulled it all together. And I find So what I'm going to use this formula here. And I know the radius and I know the angle in radians. So I know that the arc length, the amount of arc length, here's what I say, the amount of arc length which has come in contact with the ground as it rotates equals r times theta. I plug in my numbers, 0.381 meters times my answer in radians, 10.82 radians. And remember, I emphasize again, writing radians is just placeholder. It's not a real unit. Right? So when it's convenient, I will drop it. Since I want arc length to have units of meters, not meter radians, I just drop radians because that was just a placeholder anyway. So it was fake. So I can then write S equals whatever, 3.1. So it's going to be about 4.1, something like that. Multiply these.
4.1, yeah.
If I really write it out literally, I write it meters times radians. Right? Meters here, radians there. But radians is just, it's a placeholder. So it doesn't really have a, it's not a real Q. So there you go. So the arc length is 4.1 meters. And then because no slipping, I get that delta x equals s. That's what the no slipping condition will apply. So therefore, the circle travels through 4.1. Okay, that's how that goes. Okay, good. All right, so this equation is the bridge between linear motion and rotational motion. All right. Great. So that's fine. We just want to talk about positions, but what we want to do is to talk about motion, not just position. So we want to talk about rates of change of position. So we need to start taking time derivatives. So angular motion. So we need rates of change. Right? So we need to take time derivatives. So we have angles, which tell us the position on a circle. Right? That's what an angle would tell us. If I take a time derivative of it, well, that would tell us, what would that mean? It tells how many radians per second we're changing, right? So it's like a rate of change of the position on the circle. What do we call the rate of change of position? Just normal motion in this room.
Transitional.
Velocity, right? Rate of change of position is velocity. But now it's not just any motion, it's on a circle. And it's an angle. So we're going to call this angular velocity. Okay. And because we don't have anything else to do, we're going to give it another symbol. Because otherwise things would be too easy. We're going to call that omega, not W. It's a Greek letter omega. If you call it W, we all get to make fun of you. Don't do that. But what does omega mean? It's the rate of change of the angle in time. So what units would you give it? How would you measure the angle if you're going to give it a fake unit? What would it be? Radians. So this would be radians per second. So this thing should have units which are like radians per second. Okay. What if I wanted to have, so, you go around, you say, oh, if it goes around once a second, that'd be 2 pi radians per second. That's how that would go. What if I wanted to have not go around at a steady speed, but I want to allow it to start slow and then go faster, 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 faster? Well, that's a rate of change of the rate of change, a second derivative. Okay, so you could talk about the rate of change of omega or the second time derivative on theta. Oh. The second derivative with respect to time on the angle, which would be the first derivative of omega, angular velocity. Any guess what we're going to call that?
Torque.
Torque. No, it's related to torque, but we're not calling it torque. The derivative of position was velocity. So we call this angular velocity. What do we call the derivative of velocity?
Angular acceleration.
So we're going to call this angular acceleration. And the units on that would be radians per second squared. Right? And because that would all just be too straightforward and simple, we kind of have to hide our work to confuse people. And so we're going to use a Greek letter here. What is this Greek letter?
Alpha.
Can we all say it? Alpha. Can we all say it? Alpha. You know what this is definitely not?
A.
Don't you say it. We don't use the F word, remember? Right. I have people say fish and then they get made fun of. Don't do that. You said fish, but their eye is high. Okay, don't say fish, it's alpha. I assume the reason why we use omega is that in German, W and V both make a V sound, I think. And so I bet that that's a connection between why omega, right? I suspect it was that does anybody speak German? No. I suspect that that's the bridge, but that's just me guessing. It's that velocity was mixed with W, which turned into omega. Okay. The pattern is this, though. In a formula, you notice that basically that you can convert between normal linear motion and angular stuff pretty much just by going from Latin letters to Greek letters. That pattern will carry you through. You can remember that. That's kind of a guide. Sort of a dictionary between linear motion and rotational motion, just by switching Latin for Greek. As you guys already know, I don't let spelling stop me. So a lot of times, you can kind of, if you're a little confused, you can kind of think about what the formula would be if it was just motion side to side, and just swap Latin for Greek. Just change the letters with the appropriate dictionary, and it'll come out right. Okay, so we have this. So we have this dictionary going on. So let me kind of relate things. We get S, and then we have theta. Actually, I should put the S on the other side. We have theta and S. What's the connection between S and theta? S equals R theta. Now, if you take a time derivative on theta, what do you get? What's the rate of change of theta? Omega, or the angular velocity. So I can write omega here. And that would be analogous to or connected to the tangential velocity that a point on the edge of the circle would have. And the actual connection between them is, because R is constant, so just take a time derivative of both sides, and you get R omega. Because if you take a time derivative of the rate of change of the arc length, that's going to tell you the tangential velocity. And R is a constant, so you just get a time derivative on theta, which gives you omega. And then you also have alpha. Okay, that's one more time derivative. So you take a time derivative on this over here. Time derivative of the tangential velocity is going to give you the acceleration tangent to the circle. Remember, we had centripetal acceleration. That's what caused you to change direction. But you could also go faster, faster, faster as you rotate. That would be caused by an acceleration along the circle. And that is R. Take a derivative of this. You get alpha, or you get A tangent equals R, and you get alpha. Okay. So we can describe motion in lots of ways. We can describe in terms of linear quantities, things with units of like meters per second squared. Or you could describe it in terms of angular changes. And then if it rolls up slipping, the motion, the amount of arc length changing corresponds to horizontal motion across the room. Okay, these are all different ways to describe it. And you can describe in terms of horizontal motion or velocities. You can talk about rates of change of lengths around the rim of a circle, or in terms of the rates of change of the angles. All right. Now, there's one other bit of kind of definitions that will get used for the special case where the angular velocity is constant. What would that mean? If the angular velocity is constant, omega is constant, that means your tangential speed, tangential velocity is constant. Yeah. So that means you're rotating at a fixed rate. So if that's true, so this is a steady rotation. There's a different set of vocabulary that we will use. In this case, we will talk about period and frequency. Okay. Different vocabulary, right? Different kinds of motion require different vocabulary. A period is the time for one cycle. So period has units of time. And the symbol we use for period is a capital T. Capital T, not tension. Gotta keep them straight. T is a length of time for one cycle. Frequency measures cycles per second. Or cycles per time. And the symbol we use for that is F, lowercase f, not friction. Keep them straight. And no surprise, there's a connection between these. If period is time per cycle, frequency is cycles per time, the connection is that the period equals 1 over the frequency. And because of that, we deduce that the units of period is going to be seconds. The units of frequency is going to be inverse seconds. But that's a mouthful. Does anyone know the name we give for an inverse second? Hertz. Hertz. Yeah. This is measured in hertz. H-E-R-T-Z, not hertz like it hurts me to do this. Okay. H-E-R-T-Z. So that's just a lot of vocab for stuff that's not really that complicated. Let's do a problem where we do, basically it's a unit conversion problem. Okay, so all right. So, okay. If a circle rotates at, let's see here. Let's say it takes a circle 1 second to rotate. Takes, circle of radius 0.5 meters. Takes a circle 1 second to rotate. Okay, it takes it 1 second to rotate, and we'll assume it's steady, right? Uniform rotation. So there's no angular acceleration. I would like to know what is the period, what is the frequency. I don't want you to think about it. There are a couple ways you can do this, but I want you to find the angular velocity. I haven't told you how to do that. You have to think about this. And the tangential velocity, or speed. Okay, so take a second. Think about how you would do that. You know the radius, and you know that it takes 1 second to rotate around. Okay. What does period measure in words?
Time it takes for one rotation.
Period is the time for one cycle. Okay. So in this scenario, how much time did it take for one cycle? 1 second. Right? 1 second to rotate all the way around. So the period is 1 second. What is the frequency? How many cycles did it complete in 1 second? 1. One cycle per second. Writing cycle is kind of like writing radians. It's a fake. It's a counting. It's not really a unit. It's really an indication of counting numbers. Right? And we write that as 1 inverse second, or better, is 1 third. Okay. How many people had that much? All right. Now, how do we think about omega? What does omega measure? Angular velocities. What would be the units on omega? Radians per second, right? Okay. How many radians do you get for a second? So 1 second, how far did it turn? 2 pi, right? Everything's radians. 2 pi, right? Because in 1 second, it went all the way around. So, so this is going to be 2 pi radians per second. All right. Now, let's find the tangential velocity. How do you relate omega to the tangential velocity? We go back to our main equation for circles, namely that you can say that S is R times theta, or you take a time derivative, you get the tangential velocity is R times omega. So the tangential velocity is R omega, you plug in numbers, and you get 0.5 meters times 2 pi radians per second. You get pi meters per second. Okay. How many people, give me a thumbs up if you think you understand how to do that. Yes? Yes? All right. I'm going to change the numbers. I want you to resolve. Let's say instead of 1 second, let's say it was a half a second. So it takes a half a second to go all the way around. Now think about that. Is the period bigger or smaller? It used to take a second to go all the way around. Now it takes half a second to go all the way around. So is the period bigger or smaller?
Smaller.
Smaller, right? Because the time for each cycle is less. What about the frequency?
Bigger.
It's bigger, right? If it takes less time to go around, that means that each second kind of buys you a bigger turn, more cycles. What about the angular velocity? Well, it takes less time to make a full rotation, which means you must have been sweeping through more radians per second. So it's bigger. And therefore, you're going to get a bigger tangential velocity. So go through and recompute these numbers now. In this case. What do we get for the period? Half. Frequency,
2 hertz.
2 hertz. Omega.
4 pi radians per second.
And how do you figure that out?
You divide it by 1/2 instead of 1, right?
Yeah, you know you're getting, for each second, you're getting twice as many radians, right? Because you're, yeah. So you get 4 pi radians per second. Basically, you're just, for every second, you're getting twice as much of a rotation. And what do you get for V tangent? Yeah, it's just going to be 2 pi meters per second. All right, give me a thumbs up if you got those numbers. Yes? Yes? Okay, good. Now, the thing that maybe you can see, can you tell that when we double the frequency, you doubled omega? They always move together. In fact, you can always write the following. As long as the motion is steady, as long as the rotations are steady, that the angular velocity measured in radians per second is 2 pi times the frequency measured in hertz. That's always true. So that's a handy little conversion you get. It's also the in chemistry, or if you do atomic physics, it's the bane of your existence, because in atomic physics, people don't say angular velocity. They just call them all frequencies. And they differ by a factor of 2 pi. And you kind of just have to look at the formulas and know which is which, and it's annoying. And it's not a deep insight. It's just some people choose to measure cycles per second. Some people want to use radians per second. You can go back and forth for free, and they just call them all frequency. So this will sometimes be called the angular frequency. So I will always write angular velocity. But other places, this is also called angular frequency. Whereas I would always call this frequency. Okay, and if everybody always agreed to say the word angular, it'd be fine, you'd know. But then people get sloppy and then they start dropping this. And you have two different things called frequency in the same context, and it can be confusing. I will not do that, but you should know that it happens. All right. Let's stop there. That's a lot of new vocabulary. So let's finish off the lab, and then if we have time, we'll do some practice problems after finishing the lab. I think the lab will only take about 10 minutes to finish. So last time to practice solving some problems.